Welcome to the last central exercise session of this semester. As usual, hopefully we'll be answering your questions in chat. Let me just share my screen to show you that. So if you want to ask questions, then please use the chat available here. And we'll be answering or taking your questions here in this channel, MA9714-CE. Your chat moderator today is Arda once again.
Hi, everyone. My name is Arda. Most of you already know me, I guess, and I will be the chat moderator for today.
So as usual, if there is a question, then please don't hesitate to ask in that chat channel, and we'll try to answer those on air or in the chat directly. Of course, we'll also be available on that chat channel, or on the general chat channel rather, after this central exercise session. So if you have any questions when you prepare for the exam, then again, please don't hesitate to ask those questions, preferably using the chat channel, MA9714-general. Okay, let's get started with today's problem session. As usual, I'd like to first post a quick poll to see what seemed most challenging on sheet number 13. So here's the choice of problem types that were on sheet number 13. I'd like to ask you to cast your vote here. Okay, I'll give you a few more seconds. So let's close the poll. And here is the results. So it seems that Green's theorem takes the lead here. That seems to be the most challenging part. We do have a problem on Green's theorem among the central exercise problems, the last one. So maybe I'll just do that one first so that we can answer all the questions that may be circling around Green's theorem before we do the other two. Okay, thanks for the feedback. Then I guess we'll start with the last problem on the sheet for today. That is 1313. Okay, so that problem says use Green's theorem to compute the integral of a certain function. And that is the function v, the vector field rather, v, given as v of x1, x2 equals 3x1 squared and 2x1 squared x2. Along the curve gamma, and gamma is defined as the triangle with vertices 0, 0, 4, 0, and 4, 2. And the direction of the curve is counterclockwise. Okay, so let's make a quick sketch first for that triangle here. We have 0, 0. Let's say this is the origin. Then we have 1, 2, 3. That is 4 here. 4, 0. And here is 4, 2. That point. So the triangle that we're looking at is this one here. And gamma is the curve, the boundary curve on that triangle in counterclockwise direction. So we're running through that boundary in this direction here, right? That's counterclockwise. Okay, like this. Now to apply Green's theorem, let's quickly recap what that says. Basically, Green's theorem is a connection between volume integral and line integrals over vector fields. And the basic statement of Green's theorem is this. Let's say you have a vector field like in that problem statement here, and you have a curve, and you want to compute the integral of the vector field VDS along the curve gamma. Then, if this curve is the boundary of a certain set, then this is the same thing as computing the volume integral over that set of a different expression, the expression that you get by computing dv2 dx1 minus dv1 dx2 dx1 x2. Okay, so this expression here, the partial derivatives of the components v1 and v2 of the vector field with respect to either x1 or x2, both of these functions, so this one and this one, both of these are scalar fields, so they take as input x1, x2, and the output is a scalar. So here we're integrating a scalar field over that body B here. One thing you should note is that Green's theorem only works in dimension 2. And that's the only thing that makes sense for what we have learned, because we only dealt with the curve, with line integrals along a curve. If you want to generalize that to higher dimensions, you can do that, but then you have to deal with integrals over higher dimensional surfaces and not just along curves. And of course, that's a generalization that you can do. If you do that, you'll end up with Gauss integration theorem, but we didn't talk about that. Yeah, just in case you stumbled upon that, Gauss is basically a generalized version of Green's theorem. Okay, so that's what we're going to use here. The one thing that you need to make sure to apply Green's theorem is you have to make sure that the orientation of that curve gamma is correct. Specifically, the orientation has to be such that that body B or that area B is to the left of the curve as you look in direction of motion, right? So if we're moving in this direction here with the curve gamma, then on the left of gamma means here. Likewise, on that part of the curve, if we're moving in this direction and being on the left means looking here. And the same is true on that part here. If we're moving in this direction, then the left of that curve is here, right? So this here is our body B. And that's, of course, exactly what you want it to be. If that was not the case, then we would have to orientate gamma in a different way. So if you come up with a parametrization, then the orientation of gamma needs to be the other way. In this case, we want to compute the integral of exactly the right curve gamma, so we don't have to deal with that. And we want to compute that by solving this volume integral here. Yeah, so that means we're going to compute this, and the setup is just right for that. And we are going to solve this volume integral. And through that volume integral, we're going to get the value of this line integral that we actually want. Now, to solve the volume integral, what we need is a representation of B. So we want to solve the volume integral of this expression here. Sorry. That's dv2, dv1 here, of course, and dx2. So that's what we want to compute. And that means we need to do two things. The first is we need to compute this expression. And the second is we need to find a way of representing B to be able to compute that volume integral. Let's have a look at the vector field here first. So this is our vector field. And we want to compute this expression. So let's do that. It means dv2 dx1 minus dv1 dx2. So if we differentiate v2, this part here, with respect to x1, x1 appears here, then what we get is 4x1, x2. And if we differentiate dv1, this expression, with respect to x2, then, well, x2 does not appear anywhere here. So what we get is 0. Okay, so this is the expression that we want to integrate. And now we need a representation for B. Remember, B is that triangle here. As you might remember, triangles can easily be represented as normal domains usually. And this one is particularly easy. So what we have here is x1. x1 varies between these two bounds here. The first one is 0. The other one is 4. So x1 is between 0 and 4. And then x2 is basically just bound by this line here, depending on x1, of course. And this line here, the equation of that is x2 equals 1 over 2x1. Right? You can easily see the slope of that line is 1 over 2. So x2 is bound below by 0. And it's bound above by 1 over 2x1. Right? Every x2 value below that line is admissible, so it's a less or equal sign here. Okay, so that means B can be described as all x1, x2 in R2, where x1 is between 0 and 4, and x2 is between 0 and 1 over 2x1. So that is a normal domain. And that means we can compute the integral that we want. So what we want is actually this integral here. The integral of v ds over the curve gamma. Gamma is the boundary of B. So we apply Green's theorem. And we get, well, this is the integral over B of dv2 dx1 minus dv1 dx2 dx1 x2. Now we have computed that expression here. And we have the representation of B, so we can write this as a double integral. The outer integral needs to go over x1 because that is bound by two constants. So we need to integrate from 0 to 4 for x1. And for x2, we need to integrate from 0 to 1/2 x1. And the expression inside the integral is 4x1 x2 dx2 dx1. And now all that remains is actually solving that integral. So the inner integral is, let's see, we integrate with respect to x2 first. So what we get here is 2x1 x2 squared, right? Integrating x2 is x2 squared over 2, and 4 and 2 cancels out. That leaves us with a 2. And the bounds are 0 and 1/2 x1. So if we substitute those bounds, what we get is, let's see, 1/2 squared is 1/4. 2/4 is 1/2. And then we have x1 and x1 squared. So that's x1 to the third. And the lower bound is 0. So that's what we get here after the first integration step. And after the second, let's integrate with respect to x1 next. What we get is, let's see, 1/2 times 4 times x1 to the fourth, x1 from 0 to 4. So in effect, we get 1/2 times 4 to the power of 4. That is 1/2 times 4 to the power of 3. Or let's cancel out the 2 as well. That's 2 times 4 squared, or 2 times 16, or 32. So the result is 32. Okay, that completes that Green's theorem problem here. Arda, what questions on Green's theorem are there?
We actually had one question, and it is on how the parametrization would look like if we had a set that is on the right side of the boundary. So, yeah,
on the right side. So well, then we have to invert the parametrization, basically. So if you have a set that is on the wrong side of a boundary, so to say, then you just have to turn that curve around, right? If you have a curve that, let's just make a very easy curve that goes from one point to another this way. One needs to be closed, right? Let's make a circle like this. So you have a circle like that. And if the set is on the wrong side of that curve, then you just need to turn the curve around. And how you can do that depends on the parameterization, of course. So either you try to come up with a new one, or you just try to fiddle with the parameter with a t, or you just invert that direction. You can also try to have the t, instead of like let the t run from 0 to 1. For example, you could use 1 minus t as the parameter, and that run from 1 to 0 then. And turn it around in that way. So there's multiple possibilities. The easiest is probably to fiddle with that t somehow. Yeah, replace t by something like upper bound minus t, and then you invert it the direction of a curve. But it all depends on how it is defined.
So the same student also asked whether we could have an example, maybe a numerical one.
For inverting that curve, oh, we could use the circle, for example, if you want. So let's say we have gamma. So gamma of t. That first circle here, for example, this one. We've seen that already. You might remember that we had a circle that was parameterized like that: sine t, cosine of t. Like this here. And then t just ran from 0 to 2 pi, right? And the circle that you get is then a circle that starts at the point 0, 1. Then the x1, the sine coordinate, increases, while the cosine t coordinate decreases. So you start in this direction here. Right, so the circle you get is running clockwise. And the left of that circle is, of course, this outside area here. If you actually want to have the inside area of the circle, then you need to reverse its direction. And one possibility for doing that would be to invert the t if you want to. So I'd like to have that circle run backwards. Of course, that would that would happen if I started with the t at 2 pi and then decrease it instead of starting at 0 and then increase it, right? So what I could do is I could redefine this as sine of 2 pi minus t and cosine of 2 pi minus t instead. And again, have the t run from 0 to 2 pi. Then this argument here, 2 pi minus t, that would vary between 0 and 2 pi again. So you get the very same points, but it's running backwards, right? So it's now starting at sine of 2 pi. Here it's ending at sine of 2 pi. And then it's tracing its way backwards until we reach t equals 2 pi. That's when we hit sine of 0. And that's where this curve started, right? So it's the same curve, it's the same circle, but it's the direction is now reversed. So now we're running in counterclockwise direction. All right, meaning we have something like this here. So now we're starting in this direction and have the circle run that way. And now the left of that circle, of that curve, is of course just the interior of that disk. Yeah, so that's one easy way. Just invert the parameter in a way.
So I think that was a well enough answer. So one more question about this is whether this is actually relevant for the exam.
Of course, it's relevant for the exam. You know how to parameterize curves, you know Green's theorem, you should be able to apply it.
No, I mean the inverting of the curve.
The inverting of, yes, of course.
Okay.
Again, you know how to parameterize curves. So you should also be able to invert them if necessary. Of course, you can also come up with a completely new parameterization, right? So in that case, I could also have said, well, what I actually need is this circle here. And I already know a parameterization of that circle, right? I could just go ahead and say, well, this is cosine of t and sine of t, right? T in 0 to 2 pi. And that's precisely the same circle, precisely in the same direction. The only difference would be that this circle starts here, and the one that we have here, I would start at this point here. But it's a closed circle anyway, so the starting point doesn't make a difference. Yeah, and of course, you could also use this orange parameterization, this one here. So there's often multiple ways to come up with the correct parameterization. You just need to pay attention that the area you're interested in is on the left of your parameterization.
Okay, so then one more question about this question about C1313.
Yep.
So if we were to not use Green's theorem, and instead did line integrals on 3 of the lines, would that be more work or less work?
I would guess it's more work. I mean, what you have to do here is, if you really want to compute this by hand, so to say, you'd have to find a parameterization for that curve. And that means you would have to find a parameterization for that line, then for that line, and then for that line, and then evaluate those 3 line integrals.
Mm-hmm.
So in my opinion, that would be quite some work in this case, whereas computing this integral is basically a one-liner, almost a one-liner.
Mm-hmm.
Right? Of course, you have to evaluate that first, but that shouldn't be much of a problem. And you would have to come up with this normal domain representation.
Mm-hmm.
Yeah, that's probably the most complicated part here. But again, we've seen triangles, so that shouldn't be too hard. So let's just say this is the way I would use. But of course, if Green's theorem is not explicitly asked for in the problem statement, then you're free to do it some other way as well. If I'm asking you to apply Green's theorem, like here in this problem statement, then of course I'd like to see Green's theorem applied. Yeah, then any other way of computing this might get you the right result, but it's still wrong in terms of the problem statement.
Okay, so just wait a minute. Oh, okay. So if the set B is a disk and therefore the curve is a circle, then we could combine the transformation to we could use the transformation to polar coordinates and use the Green's theorem with that, right? So
Of course. Yeah, of course. Yeah, you can also combine Green's theorem with transformation of coordinates. Yeah, certainly.
Okay, so one more question is whether if we integrate a vector field over a closed curve, like a full circle, does the result depend on the starting or the end point, or is it the same for every starting and end point because the curve is simply a circle?
That depends. So the answer is for general vector fields, it might depend on the starting and then on the end point. So it might matter which point you actually choose. For conservative vector fields, so gradient fields, the integral along a closed curve is always 0. And that means it doesn't depend on which points you choose.
Mm-hmm. Okay. Okay, so I think that answered all the questions. I'm hoping I did not miss any. Yes.
Okay. Okay, great. So I suggest maybe we just go backwards and do 1312 next. Okay, so here we have a conservative vector field. And the problem statement already says that is a conservative vector field that is given by v of x1, x2 equals, let's see, 2x1, x2, e to the power of x1 squared plus x2, and e to the power of x2 times 1 plus e to the power of x1 squared plus x2 to the power of, sorry, e to the power of x1 squared. Okay, and in part A, we are being asked to determine an antiderivative, capital F, of the vector field. So capital F, there would then be a function from R2 to R. It's always a scalar field. And that function would have the property that its gradient of capital F is the vector field V. Right? So the vector field is conservative. That means it is a gradient field. That means there is some function such that the gradient of that function is our vector field. And this subproblem here asks us to determine that function. So what do we need to do that? Well, if that holds, then obviously the partial derivatives of that function f with respect to x1 and x2, that would be the components of the vector field. So df dx1 is the component 1. That means that's 2x1 x2 times e to the x1 squared plus x2. And df dx2 would then be v2 of x1, x2. Right, and v2 is e to the x2, 1 plus e to the x2 squared plus x2 e to the x2 squared. And of course, we can just use these two relations here to try and compute capital F, or one possible capital F. We'll start with this one here. And that means if the derivative of capital F with respect to x1 is this expression, then we could just integrate that with respect to x1 to get a candidate function for capital F. And that's what we want to do. So f of x1, x2 is of the form integral of v1 over x1, x2 dx1. So we just need to compute this integral here over 2x1, x2 e to the x1 squared plus x2 dx1. Now that might look complicated at first, but if you actually give it a try, you can see that if you take this part here, e to the x1 squared plus x2, and differentiate that with respect to x1, now what you get is 2x1 times e to the x1 squared plus x2. So this is exactly this 2x1 here, right? So with the exception of x2, this part here is precisely the derivative of that. So what that means is the integral is e to the x1 squared plus x2. And of course, times x2. Yeah, so we just regard x2 as a constant here. We're only integrating with respect to x1, so we can take that out. And the rest is then simply verified by just taking the derivative of this here. In case you don't see that, of course, you could also try integration by parts. Yeah, that's not too complicated either. Try and get rid of that x1 expression. Integrating that is not too complicated, hopefully. You can try that. And then do integration by parts. Or, of course, substitution. That might also work. Yeah. Try and substitute t equals x1 squared, for example. That should get you the right result either. Okay, so that is this integral here. However you come up with that. Of course, there might be more to that. I said we integrate with respect to x1. So we regard x2 as a constant. And that also means every function that only depends on x2 would be regarded as a constant. So there might still be some function depending only on x2 that we can add. If we differentiate this expression here, right, then this first part yields this expression that we actually want. And this part here, that will vanish if we differentiate with respect to x1. So there could still be a function depending only on x2. And how that would look like is what we get if we compare with this part here. So now we have a candidate for f. We can try and differentiate that candidate function with respect to x2 and then compare the result to this. And hopefully this gives us a hint about how this phi of x2 looks like. So what that means is our df of x1, x2, dx2. Let's try to differentiate that. For that part, we need to apply product rule. So that means here we get, first let's differentiate this. That's 1, and we're left with just the expression e to the x1 squared plus x2. And next, let's differentiate this expression, keep this x2. So then we get x2 times, differentiating this with respect to x2 just yields the same function again. So we get e to the x1 squared plus x2. Okay, and then there's this phi, and of course we get phi prime of x2 if we differentiate that with respect to x2. Okay, what we know is this is supposed to be equal to this expression here. So let's copy that here, e to the x2, 1 plus e to the x2 squared plus x2 e to the x2 squared. All right? Now let's see if we compare this. Actually, I think I made a mistake here, right? Right, I made a mistake here. So sorry about that. As you can see, this is an x1 and this is also an x1. It's not an x2. And I mistakenly wrote an x2 here. This is a 1 actually. Yeah, that should be it. So there's an x1 here and here as well. Sorry. Okay, now let's compare that. This here is the same as e to the x2 plus e to the x1 squared plus x2 plus x2 e to the x1 squared plus x2. And if you compare those, you can hopefully see that here we have this e to the x1 squared plus x2, same as here. Here we have x2, e to this expression, same as here. So those are identical already. So that means this leftover part here, phi prime of x2, needs to be the same as this to make things work, right? So that means phi prime of x2 is equal to e to the x2. And that in turn means we can determine phi of x2 is then the same thing as the integral of e to the x2 dx2. And of course, that is e to the x2 plus some constant, c. So that's some arbitrary constant. And that means we have determined the last part of our function f. So capital F of x1, x2 is then, let's see, we had this expression here already. So we have x2 e to the x1 squared plus x2 plus this phi of x2, and phi of x2 is e to the x2 plus a constant. So that's all possible potentials of our vector field f. And the problem only asks for one possible potential, so we can choose whatever c we want here. And that means, for example, setting c equals 0 yields one possible potential. All right, so one possible answer is f of x1, x2 is x2 e to the x1 squared plus x2 plus e to the x2. Okay, any questions so far, Arda?
There's a very interesting question. So the same concept, namely the successive integration that we used here, could we use that concept for functions of much higher dimensions and with their Jacobians?
I'm not sure what you mean with their Jacobians.
So in this case, we just worked with a gradient, which the question is probably whether we could generalize this concept, this thing we did for functions of higher dimensions from Rn to Rm, for example.
Not quite. So what you can do, of course, is you can do this with vector fields in higher dimensions, right? Now we have vector field in R2. So that means the potential is a function that depends on two variables. If we had a vector field that depended on Rn in higher dimension, like this, yeah, vector field always maps from Rn to the same dimension, Rn. And we wanted to find a potential for that one. Then, of course, that would be a function on Rn, but again, with real values. Because the potential always means the gradient of f is equal to the vector field. And we could use that same approach if we wanted to determine such a potential in higher dimensions. Again, we would use something like df dx1 equals v1, df dx2 equals v2, and so on. So we just get more relations here, n instead of 2. And then we could integrate. So that means from the first or from any other expression, we could get something like f of x is the integral of v1 dx1 plus, and then we would have a function that did not depend on x1, but possibly on all the others. So that might depend on x2, x3, and so on up to xn. And then we would do the same thing, right? We would take that candidate function. We would differentiate that with respect to, say, x2. That would give us a hint about that phi here, namely would give us a hint what d phi dx2 looked like. And we could then go ahead and integrate that with respect to x2, so that from this we get a, let's say, a refined candidate expression for f, something that we already had, plus, and now we would get, let's call that phi 2, a new function that would then only depend on x3 to xn, right? So we, bit by bit, we eliminate the dependencies on the variables, until finally, with the last one, we hopefully eliminate the dependence on xn as well. Yeah, so you could apply that in higher dimensions. It becomes a little more complicated, of course. The idea is, again, bit by bit, you eliminate one variable after the other. And that way, hopefully determine the potential. Does that answer the question?
I think so. So one more question about this is, I did not understand the question myself. So the question is whether there is a possibility to get a vector valued function if we had its Jacobian.
Okay, so what we're doing here is we're talking about vector fields, and the antiderivatives of vector fields, by definition, always need to be scalar valued functions. A Jacobian for higher dimensions would be a matrix, not just a vector. But of course, you could do something like that. You could talk about something like matrix fields or tensor fields in even more general dimensions instead of vector fields. And then if you want to do something similar, then of course the antiderivative would have to be a more general function, something that maps from Rn to Rm, right? That is possible, but it's rarely being used as far as I know. So these vector fields and therefore potentials for vector fields, that is quite common in physics and engineering. There's multiple applications of that. Tensor fields, there are applications for those as well, but I think only if you really go into higher physics. So probably nothing you will encounter.
Okay. I think that should answer the question.
Okay, any more questions?
No.
Not so far, good. So let's go into B. So in B, the question is, we have a curve, gamma. That's a curve starting from the point 1, 0, ending at the point 0, 1. And we're asked to determine the line integral VDS along gamma. Now, we already know that V is a conservative vector field. And that means it's a gradient field. So the value of that integral does not depend on the curve, but only on its endpoints. So however the curve runs between those endpoints, whether it's a line or whether it's somewhat curved or whether it's looping, doesn't matter at all. So we can just compute that integral VDS by evaluating the potential at the endpoints. And as usual, we take the upper bound first, so that's the ending point. So we would evaluate that at 0, 1, and then subtract the value at the starting point, 1, 0. So same thing as with antiderivatives in one-dimensional integration, right? Only difference is we now have a point instead of just one x value. Okay, and that's how we can make use of that antiderivative that we just computed. We know that, so scroll back just a little. Here it is. Let me copy that so we can see what we're doing here. So let's take this one here, for example. Copy that. Put it in here. All right, so that was our potential here. F of x1, x2 is this. And if we substitute the value of 0, 1 in here, so x2 is 1, x1 is 0, then what we get is 1 times e to the 0 plus 1 plus e to the power of 1 minus an f of 1, 0 would then be, well, that's 0 times e to the power of 1 plus 0 plus e to the power of 0, like this. So what we get is e to the power of 1, e to the power of 1. That one is 0, and here's a minus e to the power of 0. So 2e minus 1. And that is the curve integral. So once you have potential, evaluating curve integrals over conservative vector fields is very easily done. So that's part B. Questions about that?
Well, nothing popped up about part B yet. So I think someone's writing now. But from the previous question about tensor fields, the question is there a relationship between tensors and the rotation of vector fields?
Tensors and rotational vector fields. Honestly, I don't have any idea. Sorry. Not that I'm aware of, but that's not really my field.
Nah.
So there might be a connection that I'm just not aware of.
So I think that was it.
Okay, so then let's go on with 1311, the final one for this sheet. Getting easier and easier. So here we're being asked to integrate a function in 3 dimensions. So the function is f of x1, x2, x3 is defined as 16x3. And we're being asked to integrate that over the upper half of a ball of radius 2 around the origin. Oh, 0, 0, 0, 3 dimensions, of course. And it even says use spherical coordinates. And that's just what we are going to do. So, of course, you need to know the transformation of spherical coordinates to Cartesian coordinates. Spherical coordinates are specified by a radius and 2 angles, usually called phi and psi. And the transformation is this here, r cosine of phi. Oh, sorry, let me write that. Write phi in the same way, like this. R cosine of phi times cosine of psi, r sine of phi cosine of psi, and r sine of psi. You remember, hopefully remember how those work. Let me just give you a very quick sketch here. Okay, so if you have like x1, x2, x3, and a point. Let's say this is the point. Then this is characterized by the radius. That's just the distance to the origin, as with polar coordinates in the plane. And then you have this here. You have an angle right here between the x1, x2 plane and that line connecting the point to the origin. That's the angle psi. And then you have another angle here between the x1 axis and the projection of that line onto the x1, x2 plane. So this here is the angle phi. Right? Those are the two angles that characterize that point, and then we have the radius as well. And we want to describe the upper half of a ball of radius 2. So how do we do that? It means our domain in spherical coordinates is described as all points t, r, phi, psi with the following restrictions. Radius is 2, right? So we want the whole ball, including the interior of the ball. That means the radius is between 0 and 2. We want the whole upper half of that ball. That means with that phi here, we're rotating around the x3 axis completely. So we make a complete rotation around that. We let phi be between 0 and 2 pi. 2 pi is a complete rotation. And finally, for that psi here, we're allowing values between 0, right, in the plane. And the most we can go upwards is up to that x3 axis here. So we're allowing psi to vary between 0 and pi over 2. It's 90 degrees, pi over 2. So 0 less or equal to psi less or equal to pi over 2. Okay, so notice that if we allow that to go up here, we get the values left of that axis, so to say, in this projection left of the axis, through the rotation here in the x1, x2 plane. So we don't have to go higher than pi over 2. And if we did, that would double count some points, so we shouldn't do that, right? As an alternative, of course, we could also have extended that over here and then only done half a rotation here with the phi. That would have worked as well. Should give you the same result. Yeah, so that's one possible description of that upper half ball. There are others that would do the same. Usually, to normalize or to make the coordinates unique, you would usually restrict psi to be between 0 and pi over 2. But of course, you don't have to do that. Yeah, you could get the same points using other representations. All right, let's compute the integral. Now we need to integrate over d. And the function was 16x3. We want to integrate that dx1, dx2, dx3. Remember that with this transformation here, x3 is r times sine of psi. So what we get here, if we do this, would be the following triple integral. There's no dependence between r, phi, and psi in that case. So the area that we have is, let's say, like a box in spherical coordinates. That means we can choose whatever order we want for integrals. So for example, we could, let's say, integrate over phi as the outermost integral from 0 to 2 pi, integrate over psi as the second one from 0 to pi over 2, and integrate over r as the innermost integral. And the values that we have here will be 16 times, and that x3, remember that is r sine psi. Oops, sorry. Like that. And then we need the correction factor. That correction factor is the determinant of the Jacobian of t of r phi psi, or more specifically, its absolute value. We have computed that determinant already for the spherical coordinates. I'm not going to do this again. The result of that was r squared cosine of psi. And as psi is between 0 and pi over 2, the cosine will be between 1 and 0. So we can just remove the absolute value here because that value is greater or equal to 0 anyway. Okay. And we integrate that, we integrate that with respect to r, then psi, then phi. Okay, let's do that integration then. So what do we have? We have the integral over phi over psi pi over 2 over r. So let's first collect a little. We have 16 r to the third, right? There's one r here and r squared here. And then we have sine psi cosine of psi. And of course, you could probably integrate that by yourself anyway, but the problem statement says we can also use a trigonometric identity. That's the identity sine of, let's write this, sine psi, cosine psi equals 1 over 2 sine of 2 psi. So we can just make use of that for the integration if you want to. We have sine psi, cosine psi here. So using that, that would be the same as 1 over 2 sine of 2 psi. And again, we integrate dr, d psi, d phi. Okay, so let's actually start the integration. We have 16 here and 1 over 2 here, so 16 over 2, this is 8. Let's just take out the constant, 8. We leave the phi integral and we leave the psi integral for now. And let's compute the r integral. This part here depends only on psi, so we just copy that. And then we have r to the third. And the integral of r to the third is r to the power of 4 over 4. R from 0 to 2. D psi, d phi. Okay, now that is, let's see, r to the power of 4 upper bound is 2. So we have 2 to the power of 4 over 4. And the lower bound will just be 0. So what we get is, let's copy this 8 here, and then we have 2 to the power of 4 over 4. Let's leave this phi integral here and do the psi integral next. Integral of sine of 2 psi. The integral of sine is the negative cosine. So we get something like the negative cosine of 2 psi. And if we differentiate that expression, negative cosine of 2 psi, then we get 2 times the sine of 2 psi. So we need to add a 1 over 2, like this. Okay, and this is for psi from 0 to pi over 2, d phi. Okay, now let's see, 8 over 4 is 2, so we have 2 times 2 to the fourth, that's 2 to the power of 5 then, times integral from phi equals 0 to 2 pi. And what do we get for the cosine here? Let's see, pi over 2. 2 pi over 2 is pi. The cosine of pi is -1, so the negative cosine of pi is +1 times 1 over 2, that's 1/2. And then minus the cosine of 0. Cosine of 0 is 1, so we get -1, and again times 1 over 2. That's plus 1 over 2 d phi. So finally, 1 over 2 plus 1 over 2, that's just 1. So we have 2 to the power of 5 times the integral of 1 d phi. And of course, that's easy. That's phi with bounds 0 and 2 pi. So we get 2 to the power of 5 times 2 pi minus 0. And that means we have 2 to the power of 6 times pi, or 2 to the power of 6, that is 64. So 64 pi is our result here. Okay, question about this one.
So one question that popped up is whether you could explain again why the upper bound of psi is pi over 2. And the question also probably asks, why not pi?
I try. Okay, so basically that's a decision that I made, right? You could also do the parameterization in some other way. What I did is, the R is probably clear. What I did is I used the phi first, and I let that vary between 0 and 2 pi. So I'm rotating this thing around the x3 axis completely, one whole circle, right? Now, if I want to get every point on the upper half of the ball, it's totally sufficient to let this psi vary between 0 and pi over 2, like this. That'll give me all the points on this side here. And all the others I'll get by rotating the phi, like here, right? So imagine just take that point and rotate it around the x3 axis. You get a whole circle here, okay? And that means you get the whole ball if you vary that point between here on the plane and here on the x3 axis. That'll give you a quarter of a circle, and rotating this around the x3 axis will give you the whole upper part of the ball. If you would make psi vary between 0 and pi, going over here, then that means for points in that area here, there would be more than one possibility to express them. You could either say, I'm taking this psi here, this here, and then rotate by phi to get in that area. Or you could say, I'm taking this phi, and I stretch the psi long enough to get over there. And that means in the description of that set D, we would have those points, formally we'd have those points twice. We'd cover them more than once. And that means in the integral, they would also be counted more than once. So that would give us the wrong result. We need to make sure that our set D describes all the points that we want to cover exactly once. And that's why I'm restricting psi between 0 and pi over 2, because I already have all those other points by rotating with a phi. Okay, one different possibility would have been to allow the psi to cover all those values between 0 and pi, and then only do half of a rotation with phi. So if I restrict that, then I'm good again. That would also work. Yeah, so both of these descriptions are fine. Choose whatever you like best. But please make sure that every point is covered only once. I hope that was sufficient.
Yes, I think they understood it too. And now one more question on that is, if we wanted to integrate over the whole ball, not just the upper half, the upper bound of psi would be pi is the question. And
No.
okay.
No, if we make the upper bound, so if we have psi vary between 0 and pi, would again, we get the upper bound, but we count all points in that area twice. Yeah, the body would be the same, just the counting would be different. If you want the whole ball, then instead we would have psi vary between pi over 2 and minus pi over 2. Yeah, we need to go below the x1, x2 plane. And we would get that by negative psi values. So if you want the whole ball, we would have psi vary between minus pi over 2 and pi over 2. Okay. Other questions?
Yes, that was okay. So, okay, one more interesting question is there a way to describe an egg in R3, just like when we would describe an ellipse? So,
an egg, yeah, of course. Sure, there's a way. So I couldn't do it from the top of my head, but what you have to do basically is the radius would have to vary with the angle, right? So not with the phi angles. So the egg would be symmetrical with respect to rotation around the x3 axis. But as the phi varies, the r would have to vary as well, right? If you have a larger psi value, then you would get a larger radius. And if you have a smaller psi value, then you get a smaller radius. So if you build an independence like this, then you would get an egg shape. Yeah, basically that should give you the idea. Hopefully there is actually a problem in that sheet that does a similar thing in 2 dimensions. H1310, that describes an ellipse. It's just 2-dimensional, but you could try and extend that to getting an egg shape in R3.
So one more question, now it's exam related, is whether the students can just state the determinant of the Jacobian matrix of the transformation.
So for all the determinants that we have computed so far, and that include polar coordinates in 2 dimensions, spherical coordinates in R3, and cylindrical coordinates in R3, if you use the same definitions that we used, then you can just copy the values of those determinants that we computed, just as I did here. Yeah, no need to compute those again. That would be different, for example, if I'm introducing a different coordinate system, again, like in 1310, yeah, where you might have to come up with a new computation. And also if you, for some reason, decide to use a different notation. So especially for the spherical coordinates, I'm using this definition here. There's also definitions that interchange the roles of phi and psi. And then this thing looks a little different. Yeah. Or the domains of phi and psi might be different. And again, this transformation might be different. It will achieve basically the same things, but the values that you allow for phi and psi to get a certain point might be different. So if you copy that from some formula sheet or formula book or some literature, then you might have a different transformation, and that means you might also get a different determinant. So as long as those two fit together, you're good. But please pay attention to that. Okay, so that should answer the question, hopefully.
One person is writing something. Okay, so a question to the exam.
Yes.
Are we allowed to download the exam sheet on 2 different devices? Is the question.
You're allowed to download it as often as you want to any device you want. If that answers the question.
I think
I'm
so.
not quite sure why you want to do that, actually. But you can do that, yeah, sure. No problem. Just be sure to submit the right one then, the one including your solutions.
Okay, so 2 people are writing again.
Yes, let's give them some time to write. By the way, as long as you're writing, I can maybe make one more announcement. I'm planning on doing a Q&A session before the exam, a few days before the exam, probably. I haven't fixed the date yet. I was thinking of maybe the 10th of August. That would also be a Monday. That should be after most of your other exams, as far as I'm aware of. But if that's not a good option, then please just post a message to chat and we'll try and find something else. Once that date is fixed, I'll let you know on the Moodle course page and in our team chat.
Okay, the questions popped up.
Yeah.
One of them is, what type of calculators can we use? Can we also use the graphical ones?
Use any calculators you want. There's no way I can check that anyway, so whatever you want is fine.
And one,
as long as it's not your roommate.
the question is, the students can log into the TUM exam portal from 2 devices, right?
Yes, that's possible, yeah.
Okay.
You can log in from more than one device. Again, just be sure to upload the right sheet. Yeah, the one that contains your solution. If you somehow manage to upload an empty sheet, you're to blame for that.
Someone said that they think they have an exam on the 10th of August in Garching.
Oh, what exam is that?
They have not written it.
Maybe you could let me know that. So there was some exam I wasn't aware of. So if that's the case, maybe we'll move that to Tuesday. Again, let's just say about that date, post any comments you have to the chat, and I'll see that we can find a date that fits everybody.
The 10th of August is logistics and supply chain management and production management exam.
Okay. Logistics and supply chain. All right.
Yeah, almost everyone has that one since it's
Yeah, okay.
semester short.
So maybe we can find a time that doesn't conflict. I'll look that up, or we just move that to another day.
One more question. So will there be an exam problem sheet? So I think the question is whether there will be a recap.
A recap.
Like a recap sheet, the one we had in mathematics.
Oh, no, probably not. No, I don't think I'll be able to finish that one on time. Sorry. So what I usually do is when I try to design the exam, of course, there's some questions that I think of, but then I don't make it to the exam. I often use those for that last recap sheet. But this semester, as you know, things have been quite crazy. And I have to come up with a lot more exam questions than I thought I would have to. So we get some randomization in there. And that probably means I won't have enough leftovers for a recap sheet. If I have, for whatever reason, then there may be such a sheet, but don't count on it. I'd say probably not.
Okay, so I have got some exam dates for
Yes.
students. So on the 10th, there's logistics and production.
Mm-hmm.
On the 11th, there is the retake of financial accounting. And on the 14th, there's the retake of management science.
Well, the 14th is not relevant, right? Well, we're writing on the 13th, so Q&A after that doesn't make much sense. So it basically leaves us with the 12th, right?
I think so. And One more question is whether you will be solving previous exams. Like, I think
I'll try, yes. So there are those 2 previous exams that are posted on the Moodle page already. I tried to record a video for those. But as you can probably hear, I was a little sick last week, so no chance of recording a video you'd actually understand. I'll try to do that sometime this week.
So, yeah, we have like 3 more people who are writing.
So let's give them a few more minutes. We can stop the screen sharing in the meantime.
So apparently from the 29th to the 7th of August, they have no exams.
There's no exams, really? Okay.
I'm surprised myself. On the 13th, there is the information management exam, but on the 13th, there is the mathematics 2 exam. So
yep, I can do a Q&A an hour before the exam if you want that. It might help to increase the panic.
It's the exam for information management at 8 a.m. apparently. And
on the 13th, yeah, okay, yes. So yeah, so it's after that, right? At 11, I think.
Probably. And probably it will be over then.
Hopefully.
So one question is whether it will be possible to do the Q&A session before the 7th, since they don't have exams then.
I can do that, of course. If you don't have exams before that, we can do that.
No, one question said, one student suggests that we could make a poll here or wherever, and then students could vote for dates.
Sure, that might be a good option actually. I can set up a poll with a few options. Yes, good suggestion. Thanks.
Okay, so apparently on the 7th there is the statistics exam, which is not so much fun.
Yeah, I thought so. Yeah, Stefan told me something to that.
So some have Netzwerke für den Zahlungsverkehr on the 3rd of August. So
the 3rd is, let's just say I'll set up a poll, and then we'll hopefully find a day where most of you can attend. Yeah, we try to record the Q&A so that everyone else can watch it later. Of course, if you have a question, you should actually attend.
So the poll idea worked out.
Seems like a good idea. Yeah, we do that. Okay, anything else?
There's one more person's writing.
Yes.
Between the 29th of July, between cost accounting and the 7th of August, we have no exam. Okay, so the same thing someone else wrote, I think.
Okay, so
the same thing that same person wrote before.
Some more 30th to 6th of August might work. Yeah, we'll see. Well, I'll just post several dates between those 2, and then you can select one. Okay, wonderful. So thanks for attending the central exercise session. It has been quite an interesting semester, to say the least. It's probably going to continue that way for at least one more semester, maybe. Thanks for working with me. I hope you learned something in that Math 2 session. I'll meet you at the Q&A, and at least in a virtual way, I'll also meet you in the exam. I hope you do good. I hope you do your best at the exams, not only this one. I'm wishing you all the best for this exam period and, of course, for your future studies. And maybe we'll meet at some point in the future. Hopefully not at one of the retakes. Okay, thanks, Arda, for moderating.
Just one more question.
Yeah.
But there will be, the question is, will there be a tutorial this week? And
yes, of course. Yeah, I was just going to say, I will, of course, meet some of you at this week's tutorials. So on Thursday, this will be the last round of tutorials. We'll meet at 2 o'clock as usual, and tutorials run between 2 o'clock and 5 o'clock. So be sure to join us. Our tutors and myself will be there to answer any questions you might have. And that's where you can also meet Arda once more.